Hello again. It seems like only yesterday that I was speaking to you, but so since this is my final lecture, I can't push anything over into the next lecture. Okay, but there's some paper, and Chris will post some material on the paper, and also, of course, there's the implementation you can play with. We'll see how far I get. Okay. So what I did last time, we introduced SACS, the semi-axiomatic sequence calculus, which was a typing system for programs that read and write from memory. And we had very simple primitives. We have write, read, cat, which is allocation, identity, which is move. And I didn't write this down explicitly, but for top-level functions, we also have a call primitive. You can call a top-level defined functions on a sequence of addresses or collection of addresses. And this is the contextual modal type theory thing that I don't really have time much to talk about. But you can always ask Tesla, who did some work on that. Okay. Now, we have, in this language then, values and continuations. The values are either pairs of addresses, a tagged address, or just an address. This is for the shifts. And the continuations either take a pair, the unit, they pair a tag, take a tagged value, or they take an address as an argument and have a continuation program P as an argument. Okay. So what I didn't show you yesterday, because I wanted to show you some code and the way the translation works, is what is the dynamics? How do programs execute in this language? And since there is something interesting to be said, I don't want to skip that. So I'm going to talk about that first. And then I'm going to tell you about the negatives, because right now the only times that we have here are the positive types, right? The things that we actually usually think of being explicitly represented in memory is something you can match against, right? Concrete types. Okay. All right, so how does the dynamics work? Okay. So dynamics. And the way I'm going to present this is in a style that I think is underappreciated, which is called SSOS. Okay. It doesn't mean that you're in trouble. It just means that substructural operational semantics. Okay, that's what it means. That's something that I developed with some of my students and collaborators. You often hear the term multi-set rewriting as being a related way of presenting the rules. Okay. It's particularly suitable for this kind of semantics. So the first thing we have to think about, how do we represent the store, right? Because we read and write from the store. And for that, we have something like, let me write that line. The cell at address A1 has a small value V. Cell at address A2 has a small value V2, and so on. So we have a bunch of these things. And they're part of a multi-set, or actually a set, because these things are all distinct, of what we call semantic objects, which describe the state of the computation. Okay? And then we have some processes that are executing. So proc of P1, proc of P2, and so on. Okay? So these describe the store, and this describes the processes that are running. Now, if you interpret the semantics that I'm going to give as a parallel semantics, which you can certainly do, then all these processes are running independently. Okay, if somebody can step, they all can step, or any can step. If you do it sequentially, the way the implementation does, you can only run the leftmost process. Okay, so there's a unique process that can step. So the difference between parallel and concurrent and sequential semantics is simply the scheduler. If you always schedule the leftmost process first, it'll be sequential. If you let any of them run, it'll be parallel. If you run it in parallel, then the language, the semantics is usually described as being futures. But since I haven't implemented that, I'm going to not really talk much about that, but I wanted to mention it, that the natural semantics for all of this is futures-based semantics. Okay, so now we can look at our constructs and see what the semantics should be, okay, for these things. So let's see, what do we start with? Let's start with a cut, okay? So in substructural operation semantics, what you do is you write down a rule. So for example, we have a cut X, P, and Q. And actually, let me say explicitly here, so I don't have to do so much substitution, P may depend on X, and Q may depend on X. Okay? When I write this down on the left-hand side of a rule, would I mean that in a configuration like this, somewhere I can find this? Okay? So I'm not going to write down the whole state on the left-hand side. I'm only going to write down the things that change. That's nice and modular. I don't have to always refer to all of the state of everything because I only need to refer to the things that actually. And then the transition will replace this thing that I match against with the thing on the right-hand side. So this process of cut evolves to two processes, right? Because we're starting P, so we have a proc that executes P. Let me fill that in later. And we have a second process that executes Q. Okay? And what this means is that this process evolves to these two processes over here. Okay? Now, what do I have to do with X? I have to allocate a fresh cell. So I have a fresh cell A. Okay? But now, what about that cell A? It's nowhere to be found. Okay? So what I'm going to do is I'm going to say I have a cell labeled A, which has nothing in it yet. Just write a box for that. So that comes into this position here. So really, this is I also have other cells which have not yet been filled. They've been allocated, but not yet been written to, right? And this process job is write to this cell. If it does, then it can finish. This process here can read from that cell, but only, of course, after it's been filled. Yeah?
So is the capital V just values all this unfilled?
Yeah, that's another way to do it. You could say the thing that you can have there is either the V or it's a box, but I prefer to keep the set of small values not to have an empty value. So I'm not going to redefine my grammar, but yeah. Okay, are we good so far? Okay, so that's easy. So now we need another rule. Let's say, what about writing to a cell? So we have a cell A, which is empty, and we have a process that will write to cell A small value V. What should this transition to? Yeah? Cell AV. So let's think about this for a second. This process here terminates because I don't mention it again on the right-hand side. I replace in my configuration these two things by this single one. This thing here also disappears. The cell is no longer empty because I replace it by this thing over here. Okay, and that's about it. Okay. Yep.
I have a question about the cut rule.
Yep.
I thought it was akin to a lead binding, and as a lead binding, I don't see why P is allowed to refer to X, and why both P and Q take X as an argument.
Okay, so I purposely don't use a let syntax because it can be misleading. But X is a location. P will have to write to X, so it has to refer to it because it has this destination.
Yes.
Okay, and Q can read from it, so it also needs to refer to it because it can read from it. So both the writer and the reader for this new location have to be referring to
You
X.
cannot distinguish the special input and output arguments in the syntax for P and Q.
They will be distinguished by typing because X will here appear on the right-hand side of the judgment, and this X will appear on the left-hand side of the Q.
Thanks.
Okay. Let's see, how about a read? Or let's do identity. Okay, so if I have a process, let's see, identity for 2A from B. Okay, so what do I need over here? I need a cell B. And what does it contain? Value V. And what else do I need? I need a cell A. And what does it contain? Nothing, because it hasn't been written yet. Yes? And what do I get on the right-hand side? The cell A now contains V because I moved things from B to here. So now I have cell A contains V. And what about this cell? I deallocate that because if everything, I'm assuming for the moment things are linear, so this will be deallocated, right? So it disappears. What about this process? It also disappears. It's done its job by writing to A, right? So every process has a job, which is a destination it has to write to. When it writes to that destination, it terminates. Okay? Are we good with these rules so far? Yeah?
Just one clarification question. Do we only allow writing to empty cells or also to cells that already store a value?
That's a very good question. So in the semantics that I'm describing now, you only write to empty cells. So you can mutate a cell. Okay? The reason you might want to actually mutate a cell if you want to do reuse, but I'm not describing that quite yet. Okay? If you want to reuse a cell, then we have to change the semantics. So without the reuse, you only write to empty cells. Okay? Yeah?
So if you're not assuming linearity here,
Yeah.
would you have cell BV then?
Yes.
On the other side? Okay.
If I don't assume linearity, then I would have to copy this over so it still exists after the rule. Okay?
So ID, for now, ID is like a move. And
Yeah.
then if it wasn't linear, it's like a copy.
Exactly. But it's a very shallow copy because it just takes one address and moves it, one value, which is a small thing, according to, or moves it from one location to another. But it's not like copying a binary search tree or something like this. It just copies, it's a very shallow copy. Yeah?
So you said that when we're doing this with non-parallel processes,
Yeah.
we're considering that like an ordered list and only taking the leftmost one.
Yeah.
Are cells like an unordered list? Like we can grab a cell from anywhere?
Yeah, the cells are not ordered. The processes, if you want to sequential semantics, are ordered. So the heap can have a complicated pointer structure and so on. You don't order those. But the processes have to be in some kind of linear arrangement for sequential semantics. Okay? All right. So now we need the read. Okay? How does that work? It's actually pretty simple. You know, one of the problems in our field, maybe you don't agree with me on this, but we have succeeded if everything looks trivial, okay? Because then we have written this thing in the most simple and elegant form, right? And then a referee will look at the paper and say, this is trivial, okay? Meanwhile, you spent 5 years developing that thing to boil it down to its essence, right? So this is a language with futures, right? Very small language with such explicit stores. It looks inevitable at this point, but when we started, it looked all very different, right? So you have to keep that in mind. You don't want to artificially complicate things just to make it look deep, okay? It's very hard to convey this kind of thing that happens in our area of research. But anyway, here we go. So read from cell C. We have a continuation K. And we have a cell C, which contains the value V. Okay, so that value has been filled in, so we can read. Okay. Oops, what do we do now? So we have another process. The process has to continue, right? And what does it execute? So these are the values. These are the continuations. So what we have to do is we have to pass that value to this continuation, or this value to this continuation, this one to this one, select the branch, and this one to this one. Okay. So we have to have one auxiliary thing here that says a value V is passed to continuation K, and that gives us a process, which is the one here on the right-hand side. Okay. And we continue executing that process. And we can define it. So like if we pass a pair AB to the continuation X, Y, arrow P, which may depend on X and Y, then that's equal to P where we substituted in A and B for X and Y. We pass a unit to this continuation, then we just get P. And if we pass K of A to the continuation L of X, arrow P sub L, which may depend on X, for some label set. That's the same as P sub K, plugging in this A for this X over here. And then the last one is if you have a pointer, an address, and we have matching against to uncover that, then that's P of A. Okay, so we need this auxiliary step in this definition, okay? But except for the call, which is a kind of simple, so I won't bother with because I have a limited amount of time, this is the total semantics of it, okay? So all the dynamics and how the memory is manipulated is all contained in these rules, okay? There questions on these rules? Yeah? Oh, where does the term substructural come in? Okay, so if you have a logical framework, then it turns out that this thing, okay, that then your configuration is described as a context, and this would be, if you have this proposition in your context, tensor, if you have this proposition in the context, then this would be a linear arrow. You can replace it by that. So you can take these rules and read them in logical form, okay? But to explain in more detail would take me too far afield. But that's why it's called substructural, because these are essentially like rules expressed in linear logic, but completely unrelated to our use of linear logic in our in our programming language, which is a functional language. Yeah. Okay, so this is good. So now we want to talk about the negatives, right? Because while we do like functions, we do like objects. Well, some of us like objects. So we want to be able to see what happens with them. So let's look at the functions first. So this time I'm going to start on the logical side, and then I will look at the programs secondarily. Okay, so on the logical side, we have a rule in the sequence calculus that says if I have gamma, and I try to prove A arrow B, actually this to be precise because we're thinking of linear, that would be this, gamma together with A proves B. Okay, so that seems completely like the only obvious way you can write implication. Okay. And in fact, it's the same thing for sequence calculus and natural reduction. This doesn't really change. So the question is now, we want to derive a process expression and the dynamics that matches this rule. Okay, that's what we're trying to do. So how do we do this? Well, we start. Okay, so we have a gamma. And remember the difference between these two gammas is here usually we don't write variable names, but here we have addresses labeling each of our assumptions. Okay. Now on the right-hand side, so we have that. On the right-hand side, somewhere over here, we have a destination C of type A or B, right? Because all our judgment says you can read from here, you must write to there. So if there's an error here, you must write to it. Okay. So there's going to be a write to C, okay, of something. We don't know what that something is yet. Okay, everyone along with me here? This is what you know, right? From our general approach, this is what it should look like so far. Yes? Okay, so let's go here. So this gamma is that. Now this A we label with an X. And over here we have B. Okay, well, what do you label it with? Well, it wouldn't be the same destination C. It would be some other destination, maybe some variable Y. We don't know what that is. Okay, so it would look like this. Okay, so now we have to think about what do we actually write into this. So somewhere there has to be process P, right? So that would be the process P here. So what does the process P do? It can read from all of gamma. It can read from X. It will have to write to Y. Okay. But these are variables that are fresh here, right? They don't exist in the conclusion. They're like bound variables, just like in the usual lambda. But it's not like the usual lambda because in the usual lambda, we don't have a name for the right-hand side. So if I made that explicit, it's going to be an abstraction over X and Y. And then we continue with P. Okay? So this means you write to C a continuation, which The continuation may read from X and has to write to Y. Okay. So because we give every function a destination, and we can also give it an argument, this makes sense, right? The function that corresponds to P is going to read from X, like give you an argument, but it can also write to Y. Well, every function has a destination, so it has to write to Y. Okay, so now we have to say what is the usual left rule for this is complicated, but we don't actually have to worry about it because it's a semi-axiomatic calculus, okay? This is an ordinary rule. So the left rule from the sequent calculus, if you happen to know it, we'll ditch it and make an axiom out of it, okay? So the axiom will look something like this. If I have A arrow B, and I have A, then I get a B, okay? So this would be the axiom corresponding to the usual left rule. Now we need to say what it means computationally, right, over here. Okay, so we have this. So we have an X colon A. No, actually, I've been using lowercase a for that. We have the C colon A arrow B. So I'm just translating this by giving it names. On the right-hand side, you have a destination. Okay, I'll just label that B. And now what is the process actually doing? There's no premise, so this is like, what should the process do here? So this one, you write to everything on the left, and you read from, you write to everything on the right, and you read from the left. So it has to read from C. We read from C. Oops. Okay, what did we read from C? Well, it's got to be, what is it going to be? What has been written to C? Yeah, one of these continuations, right? Because this write, which had that type, wrote this continuation into here. So if you read, what we find is that continuation. What do we do with it? We have to apply it, right? Function introduction builds a lambda, in this case a continuation with 2 arguments. And the opposite is going to be function applications. We have to apply the function. So how do we apply this function? What do we give it as arguments? A and B, right? A because it's an argument to the function. And we have to give it B because that's going to be the destination. So we have to give it the pair AB. Okay? This is kind of inevitable, right? After 5 years of work. Okay. Okay, does that make sense? Yeah? Yeah.
In our grammar, we said that read takes a continuation as its second argument.
Yep.
It looks like we just put a value.
Yep. Okay. Very good. I was going to get to that next. So it turns out if we add the negatives, we have to be able to write a continuation to memory. And then when we read, we have to be able to give it a pair rather than a continuation. So how do we do that? Well, we say something that could be stored is storable as. Now I'm pulling a normal. I'm going to change all my things like inline. Okay. So a storable as is either a value or a continuation. And then when I write or when I read, these are going to be storables rather than continuations. Okay, so I think I have recovered at this point. Okay. But the nice thing is I already have these pieces of syntax in my grammar. I don't have to invent anything new because this continuation I already needed over there for pairs, and this I already needed for pairs. And turns out the sequent calculus exhibits that symmetry, and now I'm just using them in a different way. So the way I'm using them is this same line is also responsible for functions. Oops. Yes? And, well, this line here, maybe you can guess, maybe I don't have to show you all the details. What happens to this line here? Maybe I have to show you the details. Okay. The downshift, can you guess that? Upshift, yeah, right. That's why we have 2 arrows. And they're opposites of each other. So, yeah, sure, that has to work out. Okay. And what would be here? Yeah. Maybe this is opaque enough. Maybe I should show you this. Because in the source language and introduction, these are quite different things. Okay. Once you translate to this intermediate language, they become the same. Okay. So I'll show you how that works. So by the way, this definition here, let's change the dynamics before I go to that. So this is going to be one storable S. This is going to be another storable, S prime. And now I have to pass like S to S prime. Okay. And so I have to have the symmetric versions of these. If this is a function, I'm actually passing this in the opposite order. So take the symmetric version of this. Okay. But anyway, the fundamental thing is still the same. If this represents a function, this is the argument, this is destination. You do the passing. You substitute the argument for x and the destination for y, and so on. Okay. Okay. Let's look at the width. Okay. So first, I'm going to start again with the logical rules. The logical rules are for the binary version. And may look weird because it looks like we are reusing our resources, but we're not, because the user of this can choose exactly one, either A or B. So we have to propagate this to both sides. And the axioms corresponding to that will be this. If you have A with B, you can get A with one axiom. And if you have A with B, you can get B. You can extract the first component of a pair, or you can extract the second component of a pair. That's what these things say. Okay. So now we need to figure out what that means computationally. So for this rule, okay, let's go through this systematically. So we have a destination C of type A with B. Oh, no, sorry, actually, I'm going to make it an array. So it's this one. The lazy records, L colon A sub L, for some index at L. Okay? Now, what does this process have to do? It's going to have to write to C, right? Because whenever you do C and you have a write rule like this, the write rule is right. It's actually a good way to remember it. Okay? Write rule is right. Okay? Okay, so we write to C. Okay, now we have to figure out what to write to C. Okay. So what is the premise here? Gamma. Okay. So we have to do this for all branches. So for all L and L, we do something. So we check that P sub L, X colon A sub L, okay? That's just translating these premises into that, right? So here you quantify over the index set, and you put some X into the destination, okay? So now what do we have to write here to the destination for things to work out? Yeah, continuation. What continuation? Okay, so it's going to have P sub L in it, obviously. For each branch, what do we have? Well, we have to get L. And where does the X come from? Well, X is the destination for that branch. Okay. So in natural reduction syntax, you don't have this X. The records say you have a branch for each label, right? But in the stack syntax, you have an X here because you have a destination for each process. So that introduces this X. Okay. Now, if you look over here now, even though it's different in natural reduction, it turns out to be, well, the same in the sequence calculus because we already have that thing to represent sums. Okay, now for these, how does this work? So we have C colon, width of L colon A sub L for L element L. Okay, so this process would have to read from C, right? Okay. What does it read there?
The label destination.
Yeah, this thing here, right? It reads this continuation. So we have to pick out one of these branches. Here it's just 2, but here it could be any of the branches. So how do we pick that out? Well, we pass it k of A. But what's A? Well, the right-hand side is A sub k. So what we do is we take this continuation which was stored there. We say, okay, we'll pick the method k from that, and we give it the destination that was our destination. We're passing the buck. Now, this destination that we read will actually compute and write to A, like we were supposed to. But since we're passing a destination, now this process will actually do that for us. Okay. Okay, so, and now the reduction rule still works as before, because we're just matching a read and a write. And we're passing this, and the continuation is going to be this, and it's going to substitute the destination in for the process. So again, we don't need to change our reduction rules, and we don't need to extend our syntax. We already have everything we need for that. Okay? Yep?
Where does the K come from? Like, how do you know which K?
This is the program. The programmer decides, I'm going to select method K. So that's what the program will say. The programmer could write, you could pass any label here, right? Like, I don't know, NQ or DQ or whatever the methods allow you to do. Yeah. If you build a theorem prover on this, you won't know. And this rule is very hard to operationalize for a theorem prover, right? But if you have a program to check, there should be a K here, otherwise it's not well typed, and actually K has to be in the label set, otherwise it's not well typed. Okay? Any further questions? Okay, so I think Paul and Zina would agree that what happens here is that the sequence calculus exposes some symmetries in the language that are not so visible in natural reduction. And Girard would say that's a defect of the syntax. That's why Girard, when he originally designed linear logic, he didn't give a natural reduction formulation. He gave a sequence formulation because it's more, things are much more economical in terms of the presentation. And you know, the lazy records and sums look very different in natural reduction, but then it turns out, well, they are the same, really. Okay. So at this point, somebody asks, we have a counterpart here and here and here. Which question do you want to ask? Why don't we have a counterpart here? Okay. And we could have a counterpart here. That would be bottom. Okay. But bottom is not very useful because it means, essentially, if you give this to type to a process, it will not produce any output. Right? So because if you give it this destination, essentially, it means just run on your own behalf. We don't care. Just run. Okay. So it only uses resources. It doesn't do anything. So therefore, I didn't bother implementing that. Okay. Probably now, after the lecture, somebody's going to come up to me and say, I really need that bottom. Okay. But the problem is that all the judgments have to be generalized because what happens is that when you introduce bottom, the right-hand side could be empty. So right now, it's very nice to say gamma turnstile, you know, we have a judgment. In gamma turnstile process P will write to A colon A. But if you introduce bottom, then you also have to this gamma P, okay, execute on its own behalf. So you need to, you know, you need to generalize all your judgments, and I don't like to do that unless there's a really good reason for it. So we don't have bottom, but so let me put parentheses here. It does exist, but we don't have it in the language. Okay. Okay. Are there questions on this? Yep.
I mean, could you see bottom also as just being like the forking of the thread that doesn't terminate the first value? Or?
You could. Yep. It forks a thread that you cannot communicate with, But we don't have externally visible effects. So we'll just run, who knows, yeah. Yeah, you could, yeah, you can't exactly test termination, but so, yeah. Okay, other questions? Okay, good. So this is SACS, this is dynamics. And the way I've written the rules are for the case where things are linear. But if things are nonlinear, it was already pointed out, I just have to make sure that this cell is preserved. So you can either write it back over here, or I can annotate it. Says, when you match against this, keep it in your context. Okay, don't delete it. One or the other I have to do. But otherwise, the rules are the same. Nothing else has to change. Okay. Now, if I want to do reuse, what we do here, okay. So one way to do this, when you read from a cell like here, or what's the other case? I'm not sure if it's still up. Maybe it's here. Yeah, when you read from a cell, okay, rather than deleting it, you could put it back here and saying, now it's empty again. Okay? So you could potentially reuse it in the semantics by making sure that the cell is actually not deallocated, it's being preserved. And then where you're supposed to allocate a new one there, okay, you don't allocate a fresh one. This A, by the way, here, A has to be fresh, right? We don't want to allocate something that already exists. But then you have a version of this rule that reuses a cell that's already empty, that has the correct type, instead of allocating a new one. Okay. So it's very easy to modify the semantics to account for reuse. Okay. All right. Are we good? Yep.
I don't mean to be pedantic, but
Yep.
shouldn't all the V's be replaced with S's?
Yes. Yes. Yeah, please be pedantic. It's a very useful trait to have. Okay. Oops. Did I do everything now? Wait. Up. Yeah, I already did this one. Okay. Yep.
You said that if you reuse a cell, it needs to be of the same type.
Yeah.
Why is that?
Well, it needs to be either of the same type or it needs to be of the same size, one or the other. And I'd rather not be so specific with respect to the layout at this level of abstraction. And so the way you can guarantee that it has the same size is by saying it's the same type. Yeah. Yeah?
So when you do read over write, would they still be the same?
I'm not sure I understand the question. Okay. So now we can also try to formalize the no garbage concept, right? I had this intuition that if everything is linear, there should be no garbage left at the end, right? So what does this actually correspond to here? Any thoughts? When is computation done, actually? What does a final configuration look like? Yeah?
There are no processes left in the list.
Yeah, there are no processes. You only have cells. Right? So computation finishes when there's no more any process to execute. And you're left with a bunch of cells. And plus, they all have to be filled in. Right? Unless you do reuse, which is a separate thing, they should all be filled in. There shouldn't be anything empty because that means you were supposed to write to it and you didn't. Right? So final configuration is all cells. Okay. Now, what would this idea of having no garbage mean? Okay. So no garbage means if you start with initial configuration, which is like you have no context, you have some initial process P, which has some initial destination D0 of some type A. Okay. What would that mean? it would mean that every cell that's in your configuration is reachable from D0 essentially. Right? If you start from D0 and you go through your store, you reach everything, so everything is still live at this point. Does that make sense? For the negatives, we might have to fudge this a little bit because we weren't very explicit about building closures, but we can also say that if a variable appears in a continuation, we count it as being reachable, and then the theorem continues to be true. So basically, final configuration means only cells, no garbage means that everything is reachable from D0. Right? So everything is live. Okay, we're good on that too? If you have some mixed mode things, some are linear, some are nonlinear, okay, then of course you don't have that, but then the only linear things must be, all linear things must be reachable to from the initial destination. For the nonlinear things, there could be some things that you didn't garbage collect, so they could be left open. Now, if you were inclined to build a reference counting garbage collector, what do you think we would do here? For every cell, we would have a reference count, right? And then when we read it, we would decrease the reference count. And if it becomes 0, we would deallocate it, and so on, right? So it's very easy to build a reference counting garbage collector for this kind of thing. It takes space. And also, eventually, I want to go to a parallel language. And a parallel language reference counter, people tell me, is very bad because a reference counter turns any reader into a writer. Because when you read the cell, you then have to write decreasing the reference count. So even though something might look immutable and you're just reading it, you actually have to write to memory. And that complicates the implementation of parallelism in the language tremendously. So reference counting garbage collection is not very compatible, in a sense, with parallelism. So therefore, I'm actually probably not going to go that route. Let's build more traditional garbage collector. Yeah?
Is the reason for that complication that multiple processes might have to update the reference count at the same time?
Right. If you have contention. It's read-only contention because there might be multiple threads reading one location if it's not linear. But each of them, when it reads it, actually has to decrease the reference count. Now, the reference count becomes a point of contention. Yeah. The parallel semantics, this is so beautiful. I cannot not implement it. Okay. I must implement it. Okay. Yeah.
This is going back slightly, but you said that final configuration consists of only cells.
Yeah.
In order for us to know this, do we have to prove some sort of soundness result that it doesn't get stuck, or do you get this for free?
Very good. So if you want to show that we have preservation and progress, okay, which we do want to show, we have to show it of this relation now. In order to prove that, we have to give a type to a whole configuration, which is not difficult to do. And then I'd like to prove this syntactically. Amal is not here, okay? So then we can prove that, whenever we take a step, the type of the configuration is being preserved. And we also prove that we have progress. We cannot get stuck. If a configuration is well typed, then these reductions will always apply. And it's actually, it's a fairly simple proof. On the semantics I gave for natural reduction, it was actually hard because I was relating the expression to its final value. That makes it very difficult to prove progress because you must have a final value to even talk about it. Okay, so it's much easier on this semantics to do that. Yeah?
Are we going to talk about semantics for the up and down?
Yeah, so the up and down arrow are pretty straightforward. I can actually write them here. So if you have process, actually this doesn't change because we're just writing something arbitrary and we're reading a continuation. So the only thing I need is this last line here, which says if the value that we read is an address and the continuation expects an address, then we plug that address in for x. So it's already on the board in some sense. You don't really need anything more. So it's just, these cases here where the storables are one of these two things. Okay, other questions? Okay, then I can move to one of my very interesting discoveries. Even though probably I should credit my co-author Henry DeYoung was more his discovery than mine. So the question is, so in this data layout is fairly pointer intensive, let's say, because if you have something like A cross B cross C, just to pick a simple example, right? It would be laid out like this. There would be an address, let's see, AB, and there would be, A, and that points to something of type A, and here would be an address BC, which points to a pair, and the pair contains a B and a C, which points to a B, and this points to C, right? What I'd really like in this case is to lay it out flat. And we know at least since 1995 in Greg Morris's PhD thesis that these kind of flat layouts, they're extremely significant as to the efficiency of the code, okay? Because memory costs time in the end, and you have to follow the pointers and get worse cache behavior. There's many reasons why you'd really like to lay it out sort of like this, okay? And so I studied this stuff back in 2004, but we got stuck, okay? So we didn't come up with a good system for a logically motivated system to describe what data layout should be and what it could be. So we tried an approach using something called ordered logic. It's a weaker form of linear logic where not only do you have to use exactly every resource once, but you have to kind of use them in order. And I thought that would be cool because these things are also ordered, but it didn't work, okay? So how do we recover from that? Well, we didn't actually set out to recover from that, but we were studying the proof theory of the semi-axiomatic sequent calculus, okay? And there's a weird thing, okay? If you know the sequent calculus, you know there's a fundamental theorem you prove from it, which is cut elimination. And cut elimination basically says that you can prove anything just by using certain left and right rules that decompose the connectives, so you never have to introduce a cut when you want to prove something. Of course, if you never introduce a cut, no computation happens. That's a separate consideration. But the primary point is we can prove everything staying inside the proposition we're trying to prove. Never, lemmas are not needed, okay? But this cut elimination doesn't hold for the semi-axiomatic form of the sequent calculus. And that was a source of some consternation because we like our sequent calculus to be nice. So let's take an example here. So A cross A cross B cross C proves A cross B cross C, okay? So let's see, we want to prove this, which means writing a program which takes a memory which is laid out in this way and generate memory which is laid out in a different way, right? Okay, so how do we prove this? So we can't use the axiom because the axiom would require A cross B and C to be on the left-hand side. Right? So we can't use the axiom. So what do we have to do? Well, we have to break down the left-hand side here. So we get A comma B cross C proves that this right-hand side stays the same. What does this correspond to? We read from this cell the first and second components. Yes? Now, can we now use the axiom? No, we still can't. We don't have A cross B and C. Okay? So what we have to do is we have to read this cell. A comma B comma C proves A cross B cross C. All right, now we have decomposed this entirely. Now in local variables, we have the pointer A, we have the pointer B and the pointer C. The pointer BC in the middle, we got rid of. But we still can't use the axiom, okay? Because we don't have in our hands A cross B. So what we have to do is we have to allocate that, and we have to write this address into this part, and this address into that part. But how do we allocate something is by cut. So we use cut. We could take A comma B on this side, and proves A cross B. That's an axiom, okay? Because we have an A and a B, and we have to write that into the pair A cross B. And over here now we get A cross B together with C. And we have to prove that A cross B cross C. Okay, now this is an axiom because we have the address of the left-hand side, the address of the right-hand side, and so this is also an axiom when we're done. But what you can show is that you cannot prove this without using cut. Okay, so you need a cut somewhere because you could only use an axiom or you can use the left rule. At this point, these are the only things you can do without cut, and it would be stuck. So we need a cut. Okay, and so unfortunately, we felt like actually let me get rid of some of this stuff here. It's kind of sad that we don't have cut elimination. So the question is how to recover. Okay. And the way to recover is to say, well, we can't eliminate all cuts, but we can arrange that the cuts that remain have a very important property. And the property is that it's a cut with the subformula of what you're trying to prove. So this cut is at A cross B. And A cross B is a subformula because it occurs here. So what we could prove was that you can eliminate all the cuts except for some of them. And the ones that remain are cuts on subformulas of what you're trying to prove. So the import of the cut elimination theorem, which says we can prove everything by just looking at subformulas, that's still being preserved. Okay, even though some of these cuts remain. That was not entirely satisfactory, but it was true. And so we said, okay, something new. The cuts on subformulas, we call them SNPs, little cuts. Okay, SNPs are okay, cuts not. Okay, and then you can prove that you can eliminate all the cuts. The only thing that remains are SNPs. Okay, and SNPs are on subformulas, so it's actually okay. So this is actually not a cut really, but it's a SNP. Okay, but now we need to check subformulas. So the way we do that is the following way. If we have A cross B, then we get A and B. But we underline these because they're subformulas, so it's okay to have a SNP with them. Okay. When you have a cut that cuts out A, or this A underline or B underline, it's okay because it's a subformula of what you're trying to prove. Now we do this systematically. For example, this another axiom would be from A, you can prove A plus B. I think that's correct. That's an axiom. This is an axiom. So we underline that because it's a subformula here. And for the other one, you do the same. And then let's see, what else do we have here? Let's do some negatives. Actually, let's postpone the negatives. Okay. So these are the positives that are of interest because here, for this rule, you don't have a subformula on the other side. You don't have to mark anything, okay, because this is empty. Okay. And then the SNP rule says if I have delta together with gamma, and I'm trying to prove A, C, then delta can prove A, and gamma together with A underline, if it's a subformula, which we have tracked, then we call this a SNP. Okay? So I'm not giving you 100% of the details because I didn't show you the negatives, but it still works with negatives as well. Okay? And then you can show that you can eliminate all the cuts and all that remains of the SNPs. Okay? Yep.
Just as like a high-level proof strategy, how do you show this dependence on like needing a SNP rule that like certain cuts cannot be eliminated with a weird negative result? Like how do you go about showing that?
Yeah, you show that basically, proof theoretically, if you don't have cut, there's no other way to prove this formula. So the only rules that applies are going up are the ones that I've tried. And so you get stuck here because no rule applies. You're done. The only thing you do is an axiom. That doesn't apply. No left rule is applicable. So even syntactically, without doing anything very complicated, you can prove that you will get stuck at this point unless you can do a cut. But then it turns out, well, there's a special kind of cut named a SNP, and that's okay again. Yeah. So it turned out to be an easy proof. Yeah. The cut elimination was actually not totally easy. Okay. That you can eliminate all the cuts, only SNPs are left. That was not totally easy. That took some work. But the fact that that you need them, that you need some cuts, that was easy. Yeah. There's another way you can prove this overall, which is that you translate from this back to the ordinary sequence calculus, which is easy to do. You eliminate all the cuts in the ordinary sequence calculus. Then you translate back from the ordinary sequence calculus to this one. And you see in that translation, the only things you need to introduce are SNPs. So you can take this detour instead of proving it directly. Okay. And with that detour is actually also, that detour is pretty easy to show. But it's not very satisfying because I'm interested in how to compute. If you translate to the sequence calculus, I lose track of how to compute. So I wanted to have reduction rules directly for this. Okay. Questions? Yep.
Possibly you just covered this, but can you clarify the difference between a SNP and a cut? Because the rule looks very, very similar.
Yeah, it's the exact similar, but because A is underlined here, we know that it's a subformula of what you're trying to prove. So therefore, it's allowed. Because here, when we did this rule, this thing was something that is a subformula we're trying to prove. So we marked these as subformulas. Okay. Here A is a subformula, here B is a subformula. So then we can do the SNP. Yeah?
Going to the operational semantics
Yeah.
above for the SNP rule, can we think of this as like you're inlining the results of A when you input them into C or something like that?
Pretty close. I think, yeah, I'll show you what the semantics is for this because now I want to show you how this translates. Okay? So what do we do here? So before we did this, okay, we have a write to destination C, the pair AB. That was of type A cross B. And then here we had A colon A and B colon B. Okay? That was our previous rule for this, right? So now the following is the basic idea of this. If something is a subformula, if it's underlined, okay, then we do need to advocate fresh if we can make sure if we can calculate the address of where A and B are from the address of C. Oops, I forgot to C here. So the fundamental idea is if you know where C is in memory, we can calculate the address of A and the address of B. We don't need to allocate anything. As long as we allocate enough space for the pair, okay, rather than the following two pointers, just calculate where A and B actually are. So we're changing this rule to the following. So we're writing to C, which is C colon A cross B. And here we say it's not A, it's C dot pi 1. It has type A. And C dot pi 2 has type B. And these are underlined. And the C dot pi 1 says C has to be a pair. It has to be an address of a pair. C dot pi 1 calculates where the first component of the pair is. And if C is a pair, then C dot pi 1 will calculate the address where B is. Okay. If I do that, then this rule doesn't actually write anything. Because all this rule does, it calculates the addresses of A and B. Okay. So we still use write here, but we say, actually, sorry, I didn't mean that. Don't write anything. Okay. So in the C code, this will be silent. There won't be any rule. This write will disappear entirely in the C because in C it'll only be address computation. If you want to build a type checker, it's better to have it explicit. Otherwise, it might be difficult to type check your program. So what happens is then SNPs correspond to address computation. That's it. Cuts correspond to allocation, and SNPs correspond to address computation. And the basic intuition is that whenever you underline something, it's a subformula, therefore you can compute its address. Okay? Because subformulas mean it's laid out in a certain way. It's a subformula, so it's a piece of what you have laid out large, and so you can calculate the address of it. Okay? The only time where we have to violate that is when you follow a pointer. Because the pointer is an address, we can't calculate where it points to. We have to look it up. Okay. So even though it's a SNP, when we come to a pointer, we don't actually calculate the address, but it has to be in the program. Because otherwise you would have to lay out, all the things like sort of infinitely wide, so you can calculate, all the addresses of all the subterms. But for all the other ones, you don't actually, you just do address calculation. Okay. Okay. So for the negatives, well, actually, no, let me, I have like, I don't know, 15 minutes. So I wanted to show you how that works in the compiler. So let me just give you the raw intuition, very brief intuition about the negatives, and then I'll, yeah. Okay, so if you have a rule that says A together with A implies B gives you B, you see we're using this, but we calculate the address of this and this because these are subformulas, okay? So now we have something underlined on the right-hand side. So we calculate the destination address instead of just calculating the source address. And similarly, if you have, see, A with B proves A. Okay, so you underline this and basically says if you know where something of this form is, you know where the A has to be, okay, where the continuation address has to be, okay. So then you have another version of SNP. There's a second version where this is underlined and this is not, okay. And again, it's address calculation, but in that case, it calculates the address of a destination, not the address of a source. So everything like works very cleanly, symmetrically for all of that. So we have a positive and a negative SNP, and this is the positive one, and the negative one, this is underlined, okay. So that's how the type system works, okay. Now, okay, I want to show you some code, so I'm gonna, the negative ones, when you actually interpret these things, function calls and so on, okay, it turns into something really cool. And if I have a time to show you, I'll show you. But basically, it determines some kind of calling conventions for functions. You show where you reserve memory for the argument, where you reserve memory for the result. And then you write to these destinations and to these places, then you call the function. It knows where to expect them. Then it does its job and write to the destinations that you gave it. And so it turns out to be a very kind of cool way to compile lambda expressions, okay? That was not in our paper that Chris either posted or will post, because at that time we didn't know exactly what to make of it. But we have worked that out since then. And the compiler supports it if you give it a certain flag. Okay, so this is the code we wrote last time, okay? Okay, so I want to write a little small piece of code about lists, because lists are more interesting from the layer perspective than natural numbers. So the type of list is a choice between nil, 1, or cons, okay, standard number in this case, and another list. Okay, which function would you like to see compiled? Append? Okay, append. Okay, declaration of append of x's : list of m and, oh, I better put some arguments here, m and k. And I better guard the recursive call, standard number of mode k, and a list, again, mode m, where the elements have mode k. Okay. The fact that this is happening to me means maybe I should do some defaults for things. Okay. list mk. Let's just make all of them the same mode just to keep things simple. Get a list of mk. Okay. Definition of append x's and y's equals match x's with. If it's nil, then I return y's. If it's cons of x and x's, then it's a cons of x and append x's y's, but then I have to put a pointer to that. Okay, anybody see any typos? Okay. Let's see what happens when I run this. Snacks up on lecture 5. Okay, it's happy. That's good. It's not going to generate any code for me because I haven't said which instances to compile it at. So I need an instance of this. Instance of append. And let's say, let's make 2 modes. U, which is structural, and let's say it's greater than L. Oh, what did I do there? L. Okay, so let's append list where the elements are unrestricted, but the list itself is linear. So X is colon list L U, Y is colon list L U, and I get out a list which is L U. Okay. All right. Let's compile this. Okay, compile, that's good. So let's look at some of the output now. Let's look at the output in snacks. Lecture 5.adj.snacks. By the way, the word snacks, now I can tell you about it. As I said, it has nothing to do with food, but SACS means semi-axiomatic sequence calculus, right? I put the N there for a SNP, so we have SNPs for semi-axiomatic. Snacks, right? If you're a very fast speaker, it becomes snacks. Okay, so this is actually, here's append. Okay, so what does append actually do? Maybe I should actually, okay, so I'll try to highlight things. Okay, so it has a destination. We only compile one version of append, so it's append/0. It has a destination. It reads from the input x. If it's nil, then it reads xs.nil and matches it against the unit. Okay, that will be silent in C because the only thing that can be there is the unit element. And then we copy, okay, the y's to $0. Okay, this is actually slightly more expensive than previously because the list now is laid out more wide in a more wide thing. Right? It's laid out like this. You have the cons, and then you have the pointer to the natural number, and then you have a pointer to another list. So, so it's wider. So the copying there that has to happen in the identity actually does a little more work. Or is because it's linear, it really is a move. But yeah. Okay, so if it's a con cell, okay, then this read here, okay, calculates the addresses of the first and second component, okay, and then it reads what's at pi 1 that has to be a pointer. Remember, pointers I cannot do implicitly because I can't calculate what the pointer is, so I actually have to match against $1, which is pointed to a natural number. I read $2, which is a pointer to the tail of the list, and then I write to the cons.pi1. So that's the address of the natural number in my destination. So this actually copies the pointer to the natural number from the source to the destination. Okay. Then I create a new list. and I call a new destination, I call append with that. And I give it the argument $2, which is the tail of the list, and the same y's that came in. When I'm done with that, then $4 is going to contain the result of the recursive call. So I'm going to move that into the second slot of the pair that's associated with the cons. And then I write this thing actually doesn't do anything because I'm just doing address calculation. And then I write the cons label into the first part of the destination. And I have done the append. Does that all make sense? Is there a question on it? Yeah? Number 3. Okay, so what happened is that, remember I told you there was one optimization which I do, which you have a cut with an identity. So number 3 was something introduced by a cut with an identity, which was then eliminated by my optimization, so it disappears. Okay. Okay. So, so let's look at the code with reuse, because I think that that should be in place. Dot closure dot snacks. So this is the code for append now. And it turns out, because we have read that list, excess, by the time we get to that point in the code, we have read that list entirely. Instead of allocating something fresh for the output, we can reuse the cell 4 that came in. And then we call append recursively with that same destination. Okay. And then we continue here. So what it doesn't notice here, this is something on my to-do list. What it doesn't notice is that because we're reusing the x's, we wouldn't actually need to copy the x field over because the x is already in that field. Okay. But it doesn't reuse. We always assume that the thing we're reusing is completely empty. We don't keep track of what was in there. If you also did that and did some kind of value numbering or some kind of optimization there, you could actually eliminate, I think, at least one of these writes. Okay, but that's a further optimization that I'm planning to do at some point. But right now, it will still do some unnecessary write here. This one, okay, because that's already in the right. It's already in the right place. So that's what the append. And now we can look at the C code, lecture 5. Okay, so I've arranged here that any type in the input actually becomes a C type. That's, of course, not necessary. I can inject things into universal type and do my own address calculation. But I decided that I'm going to leave let the address calculation to C. So like, for example, the binary number has a tag field. It's a structure with a tag field, and then a union type for what could be in there. The list has a tag and then union between list 0 and list 3. And I think list 0 is going to be unit, and this is going to be some kind of a pair. Okay. The print functions, which are generated in a type-directed way, increment, and then somewhere should be append. There should be append, okay? So here, over there is the snacks code. So you can see, like, when I read, this becomes a read. When I case this, and then this read of the unit becomes silent because you wouldn't have to do that. You would have to do that in a parallel implementation, by the way, because if you have a shared cell, even if it contains a unit element, it means you have to wait until it's been written before you continue. So even though it carries some information now in the parallel sense, because this process is finished, and here it doesn't carry any information, so we make it silent. Okay? And then we do a mem copy for the identity, and that now depends on the size of the layout of the list. And if we have a cons, then we eliminate the component, we extract the components from it just by some kind of struct access. We write essentially by, again, using some kind of a path to get to the corresponding thing. Here's we have a reuse, okay, instead of an alloc. We have an append, we have a write, we write the tag, and then we're done, okay? So actually, you can see this is allocation free, right? There's no allocation happening here in this piece of code. So essentially, appending of linear lists is going to be in place. If a list was unrestricted, then of course we wouldn't do it in place. So if it were affine, what would you suspect? Can we do it in place? So head nodding, yes, we can do it in place instead of affine, right? So we're not guaranteed that it will be used, but if it's used at most once, so we can reuse that cell once we've read from it. So what this small optimizer actually just checks is that it doesn't admit contraction. Okay, then we can apply that optimization. Okay, so there's lots of examples for you to actually, if you like this kind of thing, okay, let me go and look at some of the examples. I don't know if you have actually looked around at the examples, but there's some cool ones here. So I'm going to just tell you what they are. So this is a binary search tree implementation, and there's a lot of reuse in that. In fact, well, anyway. Then we have counting down a binary number down to 0 in this representation. That's this one here. So we go to like 2 to the 22 or something, let's count down to 0. This is used as a benchmark, not because it's a useful thing to do. Some implementation of lambda calculus with De Bruijn indices, a double-ended queue with constant amortized access time on both sides. Escardo I really like. It's implementation of exact Euler arithmetic, where every real number in the interval between -1 and +1 is represented as an infinite stream of digits. The digits are -1, 0, and +1. And it turns out that Escardo is almost entirely linear, because we implemented addition and also addition, well, kind of addition, and also addition of an infinite stream of numbers. So if you have like a Taylor series or something like that, you can also do the addition on that. And it turns out to be linear. One thing in his code that was not linear when I transcribed it was this thing of, he had a function that would observe the first like n digits of a number, okay? And that's not linear because you throw away the rest. So I changed it to just observe the first n digits and then keep the stream of the remaining numbers in there. And then it becomes linear. Fibonacci sums is really fun exercise in subtyping. I don't know if you know about Fibonacci sums, but you can give a unique representation of any Fibonacci, of any natural number as a sum of Fibonacci numbers, as long as you don't have 2 consecutive ones in there. So our subtyping system can guarantee that your number doesn't have 2 consecutive ones. This is a theorem prover for intuitionistic logic that we use in our own teaching. This is KMP string matching, which doesn't have much linearity at all. This is a high-order abstract syntax representation of lambda calculus, implementation of n-queens, regular expressions. You've seen this in some of the lectures. So that's an implementation of that. So there's actually 2 regular expression matchers, one using Blazowski derivatives and the other one using continuation-based backtracking. Implementation of getting all the permutations of the list. So that's also interesting because you use lists in 2 ways. One to represent a permutation that's not linear, because you build many, many versions of the same. You have to permute, but you need to copy to do that. And then a list of all the permutations. The outer list is linear when you generate that. These are balanced ternary numbers, which are also cool. So actually, in the 1960s in Moscow, somebody tried to build a computer based on a representation. You have -1, 0, and +1 is your digits. And the nice thing is you can represent any integers in a unique way if you don't have leading zeros. So we usually represent natural numbers. But if you want to represent integers in a nice way, ternary numbers are kind of cool. And this is an implementation of tries. And tries or data structure are very linear. So some of these are more linear than others. And that's to be expected. Some algorithms with data structures have more linearity in them than others. You can look at that code and see how it works out. OK, I think that's the end of my series of lectures. But I'm Happy to entertain more questions. And I'm also sticking around for another, I don't know, 15 minutes before I fly out. So want to talk to me after.